The SpaceX Falcon Heavy is currently the world's most powerful operational rocket, capable of carrying more than twice as much into orbit as the next competing vehicle. Today, Group A204, consisting of Matt Kelly, Matthew Wright, Cole Breseman, Tarun Pillavoolathil, and Michael Coos, will discuss the development and capabilities of this rocket. The Falcon Heavy was designed to be the most powerful rocket in operation. The rocket's design uses the same engines as the Falcon 9 and uses the same technology to lift and then land. They originally intended the rocket to have payload capabilities up to 53,000 kilograms, which was around double the maximum payload of other rockets at the time. Falcon Heavy was a project completely funded by SpaceX itself. They wanted to be able to carry a large payload while being reusable, cost-effective, and reliable. The development of Heavy was mainly focused on how they could connect the boosters to the main core and successfully detach. There was a possibility that the design could support human missions to the Moon and Mars, but SpaceX has chosen to not pursue that path and instead focus on commercial satellites and other payloads.
The design of the Falcon Heavy consists of two stages. The first stage consists of three essentially repurposed Falcon 9 first stage boosters, the center core being a stretched version and the side boosters being Falcon 9 first stages with nose cones. The first stage is powered by 27 Merlin 1D engines, 9 engines per core, using liquid oxygen as their oxidizer and RP-1, essentially a refined version of kerosene, as their fuel. Each first stage booster also includes grid fins towards the top and deployable landing legs at the bottom of the booster, allowing the stages to propulsively land and be reused. The upper stage of the Falcon Heavy is the same upper stage as is used on the Falcon 9 and is powered by one single Merlin vacuum engine, running on the same liquid oxygen and RP-1 fuel and oxidizer mixes in the first stage. The rocket in general was designed to use many of the same parts and infrastructure as the Falcon 9, allowing for the reduction in components unique to the Falcon Heavy. This contributes greatly to its low cost when compared to other competing platforms.
The Falcon Heavy encountered a number of significant engineering challenges during its development, most of which are tied to the development of the Falcon range of vehicles itself. To stay specific to Falcon Heavy, I would like to highlight the difficulty of a three-core vehicle design. While it might seem simple to just bolt 2 more cores on, in 2017, SpaceX CEO Elon Musk stated that everything changes. All the loads change. Aerodynamics totally change. You've tripled the vibrations and acoustics. Later in the interview, Musk states that SpaceX had to redesign the whole center core airframe. It's not like the Falcon 9 because it's got to take so much load. However, as we're about to see, this engineering challenge and others were overcome in spectacular fashion.
This clip shows how the side boosters land after separating during the first stage. The boosters themselves are just redesigned Falcon 9 rockets and use the same technology to land the boosters on landing pads, making them reusable. This test flight widely popularized commercial spaceflight as it showed that rockets can be made more powerful while maintaining their reusability.
The specifications of each individual stage on the Falcon Heavy are similar to those of the Falcon 9. That has already been discussed though, so I'd rather take a look at some of the design choices here. The engines are Merlin 1D engines, but the second stage has a Merlin vacuum engine. What is the difference? Well, the vacuum engines have a nozzle skirt that allows for a more complete expansion of the exhaust gas. This allows the vehicle to capitalize on a higher portion of the energy in the exhaust gas. This is not used on the first stage because smaller nozzles allow more engines to be packed into the same area, improving liftoff thrust-to-weight ratio. Second, let's discuss the propellant choice. Kerosene and liquid oxygen are a classic propellant combination, seeing usage since the first Russian ICBM, the R-7. The pair is relatively safe to use, with the significant engineering challenges being handling cryogenic liquid oxygen and preventing the kerosene coking from blocking propellant pipes and turbines. The propellants are also cooled to near their freezing point, rather than kept near their boiling point. Why? Colder liquids are denser, so cooling the propellants to close to freezing maximizes the mass of the propellant that can be packed into a given volume. Maximizing this value improves the overall mass ratio of the vehicle, either boosting the final vehicle velocity or allowing for more payload to be lifted.
This diagram shows the movement of the SpaceX rocket as it ascends to deliver its payload. So initially, after the initial descent, the two boosters separate from the rocket and perform a maneuver which allows it to flip over and land and start landing right side up. It then commences on an entry burn, which slows it down as it descends back to the surface. Finally, it uses aerodynamic guidance to properly orient itself and land perfectly on the vertical landing spots. The main engine then separates and also flips over, preparing to land on a drone ship in the ocean. It too slows down using an entry burn and uses aerodynamic guidance to properly orient itself to make sure it lands perfectly on the ship without missing or tilting over. Finally, the fairing also separates, and these just fall down to the earth and are recovered at a later time. Then the payload is separated from the final rocket, and the mission is successful so far.
In 2009, plans for the Falcon Heavy were announced with an initial test date occurring sometime in 2013. But because SpaceX prioritized a variety of its other projects, the company didn't start making headway until 2013 with the construction stand for 3 of the test cores. In between 2013 and 2017, the Falcon Heavy incurred more setbacks, including the failure of the SpaceX CRS-7 mission, which failed to resupply to the International Space Station. Another issue that occurred was the unforeseen complexity of a 3-core launch vehicle, and finally a government shutdown just before launch. The Falcon Heavy finally launched 5 years after its initial scheduled launch date on February 6, 2018. For a rocket that was not expected to leave the launch pad, only 2 problems occurred. The first problem was that the middle Falcon 9 section of the rocket, or the center core, failed to reignite on descent and missed the landing pad. The second issue was that the dummy payload had slightly overshot Mars orbit at aphelion.
Aside from its highly publicized demo mission, the Falcon Heavy has flown only 2 more missions since being put into service in early 2018. These include the Arabsat 6A mission as well as the Space Test Program 2 mission. Regarding future flights, the vehicle is scheduled to fly a mission for the United States Space Force, designated USSF-44, in late 2020, with several more planned launches in 2021. Currently, there does not seem to be any intent on the part of SpaceX to retire the vehicle for the foreseeable future. However, there still remains some skepticism as to whether there will be enough demand in the future to continue to justify the operation of the vehicle, as the market for large communication satellites is slowing somewhat and the certification process for national security missions is very lengthy. The vehicle has, however, to date received orders in an amount of $500 to $700 million, which is enough to cover development costs. Nevertheless, the vehicle will continue to fly for the next several years at the very least, due to SpaceX winning an Air Force contract to supply 40% of the Department of Defense's launches through the 2020s, launching the bulk of the DoD's satellites between 2022 and 2026.
As you can see, the Falcon Heavy is the most powerful and capable rocket in the world. Its ability to use and reuse rockets allows it to be very useful in a variety of areas while also being cost-effective. Its autonomous landings also allows it to have a higher success rate than any human operator can achieve. It will continue to be used for years in the future in the commercial and defense industries.